Morning, Rock Buds. Hope you guys are doing very well. I think about you all the time and wish you such good vibes and happy times. Grammy and I are getting ready to go down to Tampa this morning, but I thought I'd make a video that's kind of different. One of my most excellent Rock Buds is from New Jersey and is interested in knowing what kind of geology happens down there. Up there, I mean. So I thought it'd be a good time to do some geology in reverse. Instead of getting a rock and trying to ID it, what if we try to find out what kind of rocks are in a specific place? So that's what we're going to do today. We're going to kind of experiment with the idea of, let's say I'm going to New Jersey and I want to know what kind of rock types I'm going to encounter up there. How do I go about figuring that out? And as usual, if you find this video helpful and you like it, please subscribe, and thank you so much to everyone who has subscribed. I really appreciate that immensely. So here we go. Investigating New Jersey geology. Okay, so the first thing we do is we hit the RockD app, which is up there on the right, to the right of the YouTube. And it gives us this, and you can see where it says map, so we press on map. And it gives us the United States. We're going to hone in on New Jersey. I'm going to find New Jersey and hone in on it. Okay, we're getting there, getting closer. But I noticed one thing RockD doesn't do very well is mark out the boundaries of the states. So I took a screenshot and I roughly mapped out the borders of New Jersey to help me see which rock types are inside of that state, our target state. So that when I go there, I'll be able to find the rock types that are indicated by these colors. So first, let's look at this huge yellow sandy section. It's actually the coastal plain. And RockD says it's the Cohansey Formation, and there are other formations here, but the main thing to note is that this is sand and clay that has not yet become rock, but will in the future. So if we look at this green color right next to the big yellow sandy coastal plain, it's more coastal plain, it's more sand and clay of the coastal plain. Englishtown Formation. The coastal plain represents areas where the sea has risen and fallen several times, depositing sand, silt, and also limey mud that will become, eventually in the future, will become rocks like sandstone, shale, and limestone. When we focus in on the blue area now, we're getting into rock. And this is mostly the Passaic Formation, and it's reddish sandstone or siltstone and shale from the early Jurassic to late Jurassic period. So I asked myself, I said, self, what was going on during the Jurassic period? This is what Wikipedia says about that. And the thing that catches my eye here is that the supercontinent Pangaea was rifting apart during Triassic and Jurassic time. The Triassic period was from about 250 million years ago to 200 million years ago, and the Jurassic period was about 200 million years ago to about 150 million years ago. A supercontinent is so big on the Earth that it acts like the top on a pot of hot boiling water. It makes it even hotter faster, and so hot molten magma from the mantle wells up and pushes straight up on the land crust. This powerful lifting and application of heat splits the crust of the supercontinent in many places. The most dramatic place is where a new ocean will develop, but there are other places that get stretched and broken, and those are called rift basins. And they're also called rift grabens, which is a German term that means basically a basin. Sediments from the adjacent high spots, which are called horsts, rapidly flow into these basins, filling them up with immature sediments, and that would be sediments that have had very little time to weather because of their rapid deposition. So let's take a look at some of these Pangea Rift Basin sediments that we find in New Jersey and the Blue Passaic Formation. Okay, so let's look at the river conglomerate. River conglomerate is a siltstone matrix which is embedded with hunks of quartz and feldspar. This is what conglomerate looks like up close. And this particular rift basin conglomerate would have a lot of feldspar hunks in it. When feldspar and quartz spend a long time in a river, being rolled and tumbled and slowly weathered down, the feldspar weathers away pretty quick, but the quartz stays there. So if we see a lot of feldspar in a conglomerate, we know that it washed into its depositional environment very quickly before much weathering could take place. And here's a road cut in New Jersey that shows some of the feldspar-rich sandstone and siltstone deposited in these rift basins. Here's a picture of feldspar-rich sandstone, and the white dots are hunks of feldspar. The presence of abundant feldspar tells you that this material was deposited quickly and not far from the original source. And here's some red siltstone from that Passaic Formation. The reddish color comes from oxidized iron, and it tells you that this siltstone was deposited during a warm, dry time when the air could oxidize the iron in the rock to a red color. Now let's look at these pretty pinkish rosy colors that the blue arrow's pointing to. Here we're looking at Precambrian basement rock that's older than 1 billion years old. This is the eroded remnant of the supercontinent of Rodinia that had been eroded down to bare rock by around 1 billion years ago and then began to rift apart between 750 million years ago and 550 million years ago. The rocks we find here are mostly highly metamorphosed rocks and represent the volcanic roots of the ancient mountains that created the supercontinent Rodinia. Here's some diorite that used to be intermediate magma intruded deep below the surface and exposed by erosion. It has a lot of quartz, a lot of sodium-rich feldspar, and a lot of biotite. If you take diorite magma and metamorphose the heck out of it, you get this rock, which is hornblende gneiss. And it's got a lot of the same minerals as diorite, but obviously it's got more hornblende. This is microcline gneiss. It's a very felsic, potassium feldspar rich rock that was originally magma extruded like granite below the surface and later exposed by erosion. This is biotite gneiss, a biotite-rich intermediate metamorphic rock that probably began as either diorite, pluton, or andesite lava and was metamorphosed. And finally, for this ancient Precambrian rock, we have amphibolite, which is a mafic metamorphic rock that probably originated as gabbro, pluton, or basalt lava before it was metamorphosed. Hey Rock Buds, so what do all these ancient metamorphic rocks tell us about continents? They tell us that continents are put together and built by the processes of subduction, and that creates volcanic activity. You get huge amounts of magma intruded into the landscape, and that magma builds pressure and breaks out into volcanic eruptions that add material to the continent itself. Okay guys, if we take a closer look at these rosy rocks, we see that in between there's these greenish stripes, and those are made of Ordovician period limestone and dolomite. When I Googled the Ordovician period, which was between 500 million years ago and about 450 million years ago, I found out that the tectonic orogeny or mountain building event occurred at that time, and so that must be related to these rocks. Let's check out limestone and dolomite. This is limestone. Limestone is made of calcium carbonate and begins its life as lime-rich mud on the continental shelf before it is pressed into limestone. Limestone is a sedimentary rock. The calcium carbonate in limestone comes from the calcium-rich shells of shell creatures and coral reefs. And this is dolomite. It's very closely related to limestone. But if you have a limey mud on the continental shelf, and then you've got a volcano that's eroding, a lot of magnesium from that volcano washes into the sea and mixes with the limey mud to form calcium magnesium carbonate, and that is dolomite. In rock buds, as you likely know, both limestone and dolomite will fizz when you drop a 5% hydrochloric acid solution on them, and that's a fantastic way to test for these two rock types. Okay, rock buds, so now let's go back in time and go through the geologic history that happened to New Jersey and see if we can put it all together and make it make sense. We begin about 1 billion years ago with the supercontinent Rodinia. All the landmass of the Earth was all connected in one giant hunk in Rodinia, and I've circled in blue what will become the United States of America. And that's where our rosy red volcanic rocks pointed to by the little blue arrow began. Hey rock buds, supercontinent Rodinia rifted apart between about 750 million years ago and about 550 million years ago, and then everything was quiet. But not for long. About 470 million years ago, the tectonic orogeny occurred, where the continent of Africa, which was then called Gondwana, was pushing and shoving and crowding the continent of Laurentia or Laurasia, which would become North America. This caused ocean crust to break and be subducted underneath another piece of ocean crust, and this created a huge volcanic island chain, represented by the purple blob in this diagram. And this volcanic island chain was very similar to the present-day islands of Japan off the coast of China. The weight of this volcanic island chain approaching the mainland pressed down on it and created a very wide but shallow sea, and that's where our limestone and dolomite were formed, represented on our geologic map by the pretty green stripes inside the rosy stripes. That wide shallow sea is called a foreland basin, and in this picture, which is a bird's eye view, it's represented by the orangey color. Hey rock buds, after the tectonic mountain building event, there were two other great events, the Akkadian orogeny and then finally the Alleghanian orogeny, when the actual continent of Africa, then called Gondwana, crashed into North America. And those activities created the supercontinent Pangaea. which lasted from maybe 350 million years ago to about 150 million years ago, and then everything was quiet. But not for long. As we talked about before, the supercontinent Pangaea began to rift apart during the Triassic period, which began about 250 million years ago, and that pulling and stretching of the crust created those rift basins that we talked about earlier, and gave rise to the Passaic Formation, conglomerates, feldspar-rich sandstone, and siltstone that we looked at earlier. Rock buds, after Pangaea supercontinent rifted apart, the ocean rose and fell several times on the continent, laying down the sands and clays and muds of the coastal plain. Okay, my most excellent New Jersey rock bud and all my rock buds, I hope this was helpful. Thanks so much for watching. Subscribe if you like this video, and this is your Rock Papa saying happy rock hunting. Papa out.